Greetings, everyone. My name is Joaly Delgado, and I am an undergraduate student in physics at the Universidad Autónoma de Nuevo León. Today, I am excited to present my research on the deposition and characterization of TiO2 thin films using DC sputtering. This study was conducted in collaboration with my professors, Dr. Michel Abraham Ruiz Robles, Dr. Francisco José Solís Pomar, Dr. María de Jesús Martínez Carreón, and Dr. Eduardo Gerardo Pérez Tijerina. To begin, TiO2, or titanium dioxide, is a material widely recognized for its excellent photocatalytic properties. Its ability to absorb ultraviolet radiation and generate electron hole pairs allows it to participate in various redox reactions, which are key in applications such as pollutant degradation, self cleaning surfaces, and antimicrobial coatings. Due to these properties, TiO2 has gathered significant attention for both commercial and military applications, especially in scenarios requiring the breakdown of volatile organic compounds and other harmful substances. In our study, we employed this sputtering to deposit TiO2 thin films. We used a Corday-Lesker DC magnetron with a 99.9 pure titanium target. The substrates utilized were new silicon 100 wafers, some silicon 100 wafers that were more than 20 years old, and silicon 111 wafers, all subjected to a controlled environment during deposition. Also, the films were deposited over Corning glass substrates to analyze optical properties. The process was carried out at varying times of 15, 30, 45, and 60 minutes, and in situ oxidation. After deposition, the films were annealed at 600 degrees Celsius for 1 hour to enhance their crystallinity and other properties. Next, we analyzed the crystallinity of the TiO2 thin films through X-ray diffraction. The results, as shown in Figure 2 of the poster, confirm the successful deposition of TiO2 on all types of substrates. The films were mostly amorphous as deposited, but they gained crystallinity after annealing, finding various crystalline phases of titanium oxide depending on the substrate. We also evaluated the optical properties of the TiO2 films using UVB spectroscopy. The absorbance, transmittance, and diffuse reflectance spectra displayed in Figure 3 highlight significant absorption of in the UV region. These results are consistent with the material's known photocatalytic behavior. The reflectance spectra suggest that the optical properties are influenced by the substrate type and the film thickness, with thicker films showing increased UV absorption. Atomic force microscopy was employed to study the surface morphology of the thin films. As illustrated in Figure 4, the surface roughness and topographical features vary significantly with the deposition time and the substrate used. Films deposited on silicon 111 showed a relatively smoother surface compared to those on silicon 100, with the roughness increasing with deposition time, likely due to grain growth during the process, but still, the films were mostly plain and showed really low roughnesses. Table 1 of the poster details the film thicknesses obtained from AFM measurements. As expected, the thickness of the TO2 films increased with longer deposition times. Films on silicon 111 substrates were slightly thinner than those on silicon 100 substrates, which could be attributed to differences in sputtering yields or surface interactions during the deposition process. In conclusion, our results demonstrate that the TO2 thin films deposited via DC sputtering exhibit promising structural and optical properties for potential applications in photocatalysis and related fields. The crystallinity, optical absorption, and surface morphology of the films can be effectively controlled by adjusting the position parameters such as time and substrate time. Further studies are needed to optimize these parameters for specific applications, as well as to explore the film's performance in real world environments. Moving forward, we plan to investigate the impact of additional sputtering parameters such as power, pressure, and substrate temperature on the properties of TiO2 thin films. Additionally, we aim to incorporate dopants to enhance the film's photocatalytic efficiency and stability. Collaborations with industry partners will also be sought to scale up the process for large area applications. Finally, I would like to thank my research team, mentors, and the facilities at the Universidad Autónoma de Nuevo León for their support in this project. I would also like to extend my gratitude to the International Materials Research Congress for the opportunity to present our work. Thank you for your attention. I would be happy to answer any questions you may have.